All right, everybody, welcome to the video here for lesson number 7 on using and working with the graphs of exponential functions. So for number 1, it says write a function equivalent to v of t by using the properties of exponent and rounding the values to nearest hundredth. So for this, we have to look here and see that 32,000 is not really part of the exponent. It's kind of like the initial value. But here I have 32,000. That's going to stay. But instead of 0.81, I could say 0.81 to the 1 over 12 to the t power. I could say that is still all equal to v of t. So that's equivalent using properties of exponents, the power-to-power property. So now if I take 0.81 and raise that to the power of 1 over 12, I get v of t is equal to 32,000 times 0.98 all to the t. Number 2 says, Jack says that p of t is representing an exponential decay function because the number in the exponent is less than 1. Comment on Jack's claim and reasoning. So let's see if he's right. So we could do this a couple different ways. We can either graph it, or we can change the base around so that the exponent's just t. So I'm going to do it that way, the algebraic way, right? Because I'm pretty sure we could all type that in the calculator and see what it looks like. So if I do 2.7 to the exponent of 0.039 and raise that all to the t, I can see what that base becomes. So if I do that, I get p of t is equal to 1.0394 all to the t, which means Jack's wrong. Because this is a growth function. Because the base is greater than 1. Now, Jack has a kind of a point. Now, I see where Jack's mistake here is. If this was a negative exponent, for sure it would have become decay, right? And sometimes because of whatever this exponent is, it might make this base become less than 1, but we have to kind of test it out and see. Number 3 asks you to graph the functions a of t and b of t on the same set of axes. So the first thing I want to do here is figure out what my scale is. So I notice my larger of the two values is 800. So if I make this, we'll say 1,000, just to be a little bit more than 800. I then can take 1,000 and divide it by the 20 boxes I have. So each box is worth 50. So I want to show that. And if I go up halfway, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would be 500. And then we could go from there, right? 500, each box is worth 50, so I have 600, 700, you get the idea. So then if we start to graph here, so let me just put these in my calculator. I'm not going to pull up the calculator screen here. I think we can all put this in our calculator the right way. Just make sure in the exponent, if you have the older calculator, you might want to use a parenthesis. And if you graph both at the same time, you'll be able to see what their intersection point is pretty quickly. But we could go right into our table of values here. So for a of t, the first value is at 800. Then we have to figure out, well, how far across do we have to go here before we get to close to 0? So it looks like in my table of values, my intersection point is happening somewhere, I don't know, somewhere in like the 7, 8, 9 range. Let's make this go out to 10. That should be good enough. So if that's 10, 20 boxes represents 10, so each box is a half, so we can make every 2 boxes represent 1. That'll be a good scale for us, I think. We shall see. One thing about making a scale is sometimes, you know what, you just guess wrong, and that's okay. All right, you can always redo it. All right, so if we start at 800, that's our first point. At 1, I'm at 565, so here's 500, and a little bit more than half. At 2, I'm almost at 400, so I'd be like here. At 3, I'm at 280. So I have 1, 2, 80. At 4, I'm at almost at 2. 1, 2. 140. At 5, 50, 100, 150-ish, a little bit below that. Almost at 100. And again, you're getting all these values right in your calculator, and you can start to see what it looks like. So you see this is going to smooth curve come down, and it's not going to touch the x-axis. Then if we go through and graph the other one, actually let me label this A of t. I like the label at the end. I think it just makes everything easy. You label however you feel you want to. All right, so if we go back here to the beginning, 400. And 317. 1, 2, 3, a little bit more. 3. 250. 1, 250. 200. 1, 2. Look at that. We're almost at an intersection. 150. 150. 125. 125. And at 6, we're almost at the same exact value. And then 79. And we can see what this graph is going to look like now. It'll look something like that. Doesn't have to be perfect. We're just sketching. Now to find this intersection point, I need to use my calculate menu, right? So we're going to say second, calculate. We're then going to go down to option 5 for intersect, and then enter 3 times. Right? So we'll go second trace and do all of your steps here. All right, you have to have everything graphed first. Now, the one thing about this is you do have to have the graph actually showing, right? You can't just start hitting enter and all that stuff. So I'm going to make my X-min and X-max, what I have on my graph paper, 0 to 10, Y-min from 0 to 1,000. This way, when I hit graph, I can actually see what the function looks like. That would make the most sense to us, right? And then once the graph is done on the calculator, you could estimate essentially where the intersection point is, somewhere, you know, around that 6 area, right? So now we can say second trace, intersect, enter 3 times. And we can see our point of intersection is at 5.987, comma 100.262. I'm just rounding out 3 decimal places. It does ask us to find the value of t that makes this work. So the value of t is just the x value, nearest whole number, so t equals 6. That's it. Quick and easy video. Hopefully that helped. Right? We'll talk more about word problems tomorrow in class. Good luck with your homework.